Hello, 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 hello. Hello. Hi everyone, we are going to explore one of the key aspects of thermodynamics today. So let's look at what thermodynamics is. Thermodynamics is defined as the field that deals with the quantitative relationships between different forms of energy. Right, so we're going to explore how that is possible, and we'll also see very clearly what are the key concepts in thermodynamics. So thermodynamics can help us predict whether any given chemical reaction can occur under a given set of conditions. It helps us predict the extent of the reaction before the equilibrium is attained, and helps us deduce some important laws like chemical equilibrium and so on and so forth. So the basic concepts associated with thermodynamics are as follows. We have the very first concept here, which is that of the system. So a system is the part of the universe that's chosen for thermodynamic consideration to study the effects of temperature, pressure, etc. And the remaining portion of the universe, excluding the system, is called the surroundings. So a system usually consists of a definite amount of one or more substances and is separated from the surroundings by a real or imaginary boundary through which matter and energy can flow from the system to the surroundings or vice versa. So if you look at the types of systems, they're divided into open systems, closed systems, and insulated systems. Open systems are those which can exchange both matter and energy with the surroundings. For example, if you take water in an open vessel, or if, say, some reaction is allowed to take place in an open vessel, for example, between marble and hydrochloric acid, an exchange of both matter and energy takes place between the system and the surroundings. And animals and plants are also viewed as open systems from the thermodynamic point of view. Closed systems. So if a system can exchange energy only with the surroundings, but it cannot exchange matter, then it's called a closed system. A closed system, for example, water placed in a closed metallic vessel, and a reaction which is allowed to take place in an enclosed, cylinder, which is closed to the external surroundings, or it's sealed with a piston, then the vessel is closed, so no exchange of matter between the system and the surroundings takes place. However, as the vessel has conducting walls, exchange of energy can take place between the system and the surroundings. So if a reaction is exothermic, then heat is given by the system to the surroundings, and if the reaction is endothermic, the heat is given by the surroundings to the system. If the reaction is accompanied by a decrease in volume, mechanical work is done by the surroundings on the system. And if the reaction is accompanied by an increase in volume, then mechanical work is done by the system on the surroundings. So as mechanical work is also a type of energy, movement of the piston in or out also amounts to exchange of energy between the system and the surroundings. So isolated systems are ones in which the system can neither exchange matter nor energy with the surroundings. And for example, water placed in a vessel which is closed as well as insulated, and where no exchange of matter or energy takes place between the system and the surroundings is called an isolated system. Tea placed in a thermos flask is an example of an isolated system, where tea, if it were placed in a closed steel pot, is an example of a closed system, and a tea placed in an open cup is an open system. So state variables and state of a system. So state of a system primarily means the condition of the system, right? It's described in terms of observable or measurable properties. Typically, the three that we would be interested in, or which we would keep seeing frequently, is temperature, pressure, and volume. Temperature, pressure, and volume. These are the three variables that we typically keep seeing, which are used to describe the system. If any properties of the system changes, the system is said to be in a different state, and the state of the system changes. That's why the properties that are shown here, temperature, pressure, and volume, are called state variables. All these three are together called state variables. A process is said to occur when the state of the system changes. The first and the last state of the system are called the initial state and the final state. A physical quantity is said to be a state function if its value depends upon the state of the system and does not depend on the path by which the state has been attained. Let's take an example. For example, a person is standing on the roof of a five-storied building, right? He has a fixed value of potential energy. So this value that's there is irrespective of the fact whether he reached there by the stairs or by the lift, right? So potential energy of the person is a state function. On the other hand, the work done by the legs of the person to reach the same height is not the same in two cases, right? Whether he went by the lift or by the stairs. So work is not a state function. So it's called a path function. A physical quantity is said to be a state function if the change in its value during the process depends only on the initial and the final state of the system and not on the path or route by which the change has been brought about. Examples of physical quantities that are state functions, they include pressure, volume, temperature, internal energy, enthalpy, entropy, free energy, etc. Volume is a state function because change in volume of water, say in a pond, is independent of the route by which the water is filled, whether it's by rain or by tube well or both. Similarly, temperature is a state function because it doesn't matter how the temperature has been attained by heating or cooling. And also the change in temperature, say from 25 to 35 degrees, does not depend on the path through which the temperature increase has been attained. Only depends on the final and the initial temperatures. Macroscopic systems and macroscopic properties, or extensive and intensive properties. So if a system contains a large number of chemical species, atoms, molecules, or ions, then it is called a macroscopic system. So the word macroscopic typically means large quantities, and thermodynamics does not deal with the properties of individual atoms and molecules, but deals with matter and bulk. Such properties of the macroscopic system like temperature, pressure, volume, density, melting point, boiling point are called macroscopic properties or thermodynamic properties. So macroscopic system has two different types of macroscopic properties. The first properties are called extensive properties, and the second set of properties are called intensive properties. Extensive properties are those that depend upon the quantity of matter contained in the system, right? So they depend on the quantity of matter in the system. Whereas your intensive properties, they are independent of the quantity of matter present in the system. So examples of extensive properties include an internal energy, enthalpy, entropy, Gibbs free energy, etc. Right? Mass, volume, heat capacity, all these depend upon the quantity of matter. Right? Mass, volume, internal energy. Whereas if you look at the second set of properties that are intensive in nature, they do not depend on the amount of substance present, but rather only on the nature of the substance. Examples are temperature, pressure, then we can even look at pH. These are all examples of intensive properties. Because pressure and temperature are intensive properties independent of the quantity of matter present in the system, that they're frequently used as variables to describe the state of the system. So it's of interest to know that an extensive property may become intensive by specifying unit amount of the substance. For example, say mass and volume are extensive properties, but density and specific volume are intensive properties of the substance or system. Similarly, heat capacity is an extensive property, but specific heat is intensive. Right? In general, the ratio of two extensive properties is always an intensive property. So to understand why volume is extensive but temperature is intensive, consider, say, a closed system of volume V containing a gas at temperature T. If a partition is put exactly in the middle, each part will have volume V by 2, but the temperature of both the parts will remain T. So the next concept we're going to study here is thermodynamic equilibrium. What is thermodynamic equilibrium? A system is said to be in thermodynamic equilibrium if its macroscopic properties like temperature, pressure, etc. do not change with time. What is a thermodynamic process? A thermodynamic process is said to occur when the system changes from one state, which is the initial state, to another final state. And the different properties commonly met within the study of chemical thermodynamics are as follows. The first type of property is called an isothermal process. An isothermal process. An isothermal process is a process which is carried out in such a manner that the temperature remains constant throughout the process. Constant temperature. Obviously, when such a process occurs, heat can flow from the system to the surroundings and vice versa in order to keep the temperature of the system constant. The second one is called an adiabatic process. So when a process is carried out in such a manner that no heat can flow from the system to the surroundings or vice versa, system is completely insulated from the surroundings. That's called an adiabatic process. The third type is an isochoric process. Isochoric processes are ones where the volume of the system is kept constant. The last type of process we study is an isobaric process, where the pressure of the system is maintained. The four processes can be represented in a graph as follows. So if you plot a graph of pressure versus volume, you can clearly see that an isobaric will be parallel to the x-axis. An isochoric will be parallel to the y-axis. Isothermal will be a downward sloping curve. Finally, if you look at adiabatic, there's a slightly um, more steeper curve. So an isothermal process occurs when the system has conducting walls, right? The container with conducting walls is called diathermic, and the walls is called a diathermal wall. And an adiabatic process occurs when the system has non-conducting or insulated walls, and it's called adiabatic walls, and the container with non-conducting walls is called adiabatic. So there are various types of processes mentioned above, and we can processes are typically of different kinds. So the first type of process is a reversible process. We'll study a reversible process now. So let's take a system which consists of a beaker fitted with a piston, movable piston that is, and there is some gas inside the beaker, and you have placed some amount of sand on the top part of the piston. So imagine the gas confined within a cylinder provided with a frictionless piston upon which you've piled some very fine sand. And you suppose the piston exerted a pressure on the gas due to its weight. So does the pile of sand, and so does atmospheric pressure. All these three have to be balanced by the pressure exerted by the gas on the piston in order for the system to be in equilibrium. Under these conditions, the piston does not move at all, and the state of equilibrium is said to exist. Now, if one particle of sand is removed, the gas will expand very slightly. But the equilibrium will be restored almost immediately. So this change is called an infinitesimal change. If the particle of sand is replaced, the gas will return to the original volume. By continued removal of particles of sand, the gas can be allowed to undergo finite expansion, but each step in the expansion is an infinitesimal one and can be reversed by an infinitesimal change in the external conditions. So at all times, the equilibrium is restored immediately. So the necessary condition for reversible compression is P external, or pressure external, is equal to pressure internal plus dP. And that for reversible expansion, this is for reversible compression. Reversible expansion is P external is equal to P internal minus dP. A reversible process is a process that is carried out infinitesimally slowly so that all changes occurring in the direct process can be exactly reversed and the system remains almost in a state of equilibrium with the surroundings at every stage of the process. A process which does not meet the above requirements is called an irreversible process. It's defined as that which is not carried out infinitesimally slowly, so that the successive steps of the direct process cannot be retraced, and any change in the external condition disturbs the equilibrium. So let's start looking at some major thermodynamic quantities. The first thermodynamic quantity that we'll be looking at is internal energy. It has been mentioned already, right? Whenever some process occurs, it's usually accompanied by some energy change. The energy may appear in different forms like heat, light, work, etc. So the evolution or absorption of energy in different processes shows that every substance may be associated with some definite amount of energy. The actual value of energy of which depends upon the nature of the substance and the conditions of temperature, pressure, volume, composition. There's a sum of different types of energy associated with atoms and molecules, like electronic energy, nuclear energy, chemical bond energy, potential energy, and kinetic energy. Right? So kinetic energy again can be the sum of translational, vibrational, rotational energy. So we typically denote the internal energy of a certain substance or as U or E, and it's equal to EE plus EN plus EC plus EP plus EK. So the energy that is stored within a substance is called its internal energy. No doubt every substance is associated with a definite amount of internal energy, but it's not possible to find their absolute value, right? Because it involves certain quantities that cannot be easily measured. However, it is not required to know the absolute value of internal energy possessed by any substance or system. What is required is the change of internal energy, right? When reactants change into products or when a system changes state from the initial state to the final state. And this is measured by delta U or delta E. So if the internal energy of a system is its initial state U1 and the final state is U2, then delta U is given by U2 minus U1. The internal energy of a system changes when heat passes in or out of the system, work is done on or by the system, and matter enters or leaves the system. Internal energy is a state function, and it depends only on the state of the system and is independent of the method by which the state has been attained. For example, if we take 1 mole of carbon dioxide at 300 Kelvin and 1 atmospheric pressure, it'll always have the same internal energy, irrespective of the fact that it has been brought to these conditions from 500 Kelvin and 5 atmospheric pressure, or from 1000 Kelvin and 10 atmospheric pressure. So internal energy is a state function. Consider an example of a system containing a certain amount of water in a thermos flask or in an insulated beaker. So let's change the internal energy of the system by doing work called adiabatic work, right? This is done in two ways: by doing mechanical work of 1 kilojoule by, say, rotating a small set of paddles, or by doing electrical work with the help of an immersion rod. In each case, the temperature is found to be rising by the same value from T1 to T2. So the same amount of work done, irrespective of the fact how it was done, produces the same change in state as measured by the terms of the temperature change. So delta U is U2 minus U1, which is the work done. So obviously, if U1 is greater than U2, the extra energy possessed by the system in the initial state would be given out and delta U will be negative. Similarly, if U2 is greater than U1, the energy will be absorbed in the process and U2 will be higher, or delta U will be positive. So delta U is negative if energy is evolved, delta U is positive if energy is absorbed. The units of U or E is ergs or joules, ergs in CGS units and joules in SI units. Two more important points about internal energy are: internal energy depends on the quantity of the substance contained, so it's an extensive property, and internal energy of ideal gases is a function of temperature only. So in isothermal processes, as the temperature remains constant, there is no change in internal energy of an ideal gas. This is because the molecular forces of attraction, the molecules of an ideal gas, are negligible. So no work is done in overcoming the intermolecular forces when the ideal gas expands. Hence, its internal energy remains constant at constant temperature. Work is said to be done whenever the point of application of a force is displaced in the direction of the force. If the force is F in magnitude and dl is the displacement of the point of application in the direction in which the force acts, work is equal to F into dl. The above type of work is mechanical work. We say W is F into dl. It's mechanical work. However, there are other forms of work, but in each of these forms, work done is nothing but the generalized force into a generalized displacement. Electrical work, say the generalized force in the EMF and the generalized displacement is the quantity of electricity flowing through the circuit. So electrical work done is EMF into quantity of electricity. So work of expansion or compression or pressure volume work. So this type of work is involved in systems consisting of gases. This is the most important type of work used in the study of thermodynamics. It's the work done when gas expands or contracts against external pressure. It's a kind of mechanical work, and the expression for such a work is derived as: consider gas enclosed in a cylinder fitted with a frictionless piston. Okay, we want to first depict that.